Okay. Hey everyone. Yeah, so we're gonna start now. Um, okay. So the first thing that we're gonna do is we're gonna look at yesterday's problems. So, does anyone have any? So, does anyone have a solution to problem A that they would like to share? I know a lot of people did get it. So, um, does anyone want to share the solution to problem one? Oh, for the link to the Code Forces group, uh, you can just go here. Okay, so for scanner, you should use print writer and buffered reader. That's much faster, and generally scanner will get you into like a bunch of um TLEs and stuff. Yeah, you can open your video, but you don't need to if you don't want to. Um not diamond collector. It's this poem. Oh, um okay, so anyways, does anyone have a solution they would want to share? Like if you have a Java solution that got TLE, or if you had a C++ solution that worked. Does anyone want to share what they did for this problem? Sure. Yeah, you can share. So you can like unmute and then explain your solution. Um, yeah. Okay, so Xie Song, can you share your solution?
Yeah. First I just went from a for loop from 1 to n.
Okay.
And then for n minus I times, I did a dot. For 2 times I minus 1 times, I did a hashtag. And then I did n minus I times dot again. And then I did a backwards for loop.
Okay. So wait, do you know how to annotate?
Uh, like this.
Yeah. Yeah,
Okay.
so try like writing your solution down so that yeah, everyone can see it.
Okay.
Or not like writing the code itself, but like writing the logic behind your code.
I mean, it's pretty simple.
Yeah, like just like trying
Dot,
to
dot,
explain your logic. Yeah.
dot, right? And then what? Yeah, there's a hashtag here. Dot, 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 dot. I noticed that here. Just
Okay.
I'm typing. Can you see that?
Uh Not yet. Okay. Yeah, okay, that works. Yeah. Okay. And then Okay, yeah, that okay, yeah. So you do that for the first half, and then after that, you can flip it for the second half, and that works, right? Yeah. Okay. That's very good. Round of applause for Xue Song. Uh, I think you can react with like here. Yeah. Okay. Yeah, that's a great solution. I had a different solution to the problem, so I'll explain my solution. My solution was basically My solution was basically to create a grid that's 2n minus 1 by 2n minus 1. And now within the grid, either it's a dot or it's a hashtag. So basically, I just wrote a condition that would be able to figure out whether it's a dot or a hashtag. And the way I did that was I analyzed what happens at the borders of the hashtags. And what happens at the border of the hashtags is that the left border can be described by a certain inequality, the right border can be described by a certain inequality, and at the end, you just need to satisfy four different inequalities in order for in order for it to be a hashtag. So if you look at my code, it looks like this. It's really short because um, if you observe, like the first one is the top left corner, and the next one is the bottom right corner. I believe. Wait, no, no. Oh, wait, no, no. The first one is the top right. The second one is the bottom left. The third one is the top left, and the fourth one is the bottom right. And if you put all three inequalities together, you'll get the correct shape. So yeah, this solution also works. Um, yeah, are there any questions about the first problem? Oh, so if you notice, I'm using I and J within the code. I'm declaring them within the for loop. So if you declare a variable within the for loop, it exists as long as you're within the for loop. When you exit out of the for loop, they don't exist anymore, basically. So yeah. Uh, hmm. Yeah, it's that should be fine. If you don't understand how it works, you can basically check the previous lecture, but I'll give you like a brief, very brief, like explanation of what this does. So a for loop, it basically allows you to do three statements. The first one, you do it once. The second one is basically the condition that you check to make it keep working. And the last one is what you do each time afterwards. So if you notice the first one, I'm declaring a variable. The second one, I'm basically making sure that variable doesn't exceed a certain limit. And the third one, I'm just incrementing it each time so that I'm doing that. I mean, that should be fine. You just need to check the lecture in the first uh, lecture, and like I explained all of that. Yeah. So this is all standard input, standard output. Yeah. Um, I don't really want to delve too deep into questions about code. Um, but yeah, I don't really want to do that too much. But essentially, this is the this is like a code that works. And oh yeah, uh, uh, it's okay if you don't understand so far. If you looked at yesterday's like recording, you should be able to figure it out. But I'm not gonna like go too deep into this now. Yeah. Um, okay. Uh, okay. So does anyone want to uh send their solution or explain their solution to problem B, preferably not the same person as last time? Anyone? Okay, so if no one has any, or if no one wants to share their solution, um, I guess I'll just explain how to do it. So essentially, the idea is that you want to do basically a brute force through all of the different points, and then and then you basically check for each point how many of the ones next to it have the same number as it. So yeah, and then the way you implement it is just you use two for loops and an array, and then you just like check it. So here's the code. It's a bit small, but um, yeah, this is something that works. Okay. Uh, um, okay. Um, anyways, is everyone fine with moving on now? Oh, the second question was just this. So this was the question we were talking about. So yeah. Okay. I guess let's move on. So the first thing that we're going to be talking about today is complexity analysis. Complexity analysis is essentially a way to calculate how much time your program is going to take before you even like code it up or you test it against a sample or something like that. It's a really neat way of being able to tell like whether your program is going to be able to pass a specific problem or something like that. So it's a very useful tool to have. And yeah, so how do you do that? Well, time complexity, like what even is time complexity? Time complexity is just a measure of the magnitude of the number of operations that your program will take. What does that mean? Well, let's say that your program has two nested for loops, each like that will go for n operations. That means your time complexity is n squared because you're going to execute the block in the middle n squared times. Um, and in this assessment, we only care about the magnitude. So for example, if your program is expected to take around 3 times n operations, the time complexity of that program will be O of n. And this is the same with like, if your program is expected to take n plus 10 operations, your time complexity is still O of n because the 10 is insignificant. Another example of this is like if you have O of n squared plus n, you ignore the plus n because that's a lower order of magnitude than n squared. So that's basically how you find the complexity of your program. Um, yeah. Yeah. Well, how do you calculate your time complexity? Between bronze and gold, time complexity can mostly just be calculated through multiplication. You just multiply all of the like nested for loops or whatever that you have. So for example, if you have 3 nested for loops, then your time complexity is just n cubed. If you have 2 nested for loops and the middle operation takes O of log n time, then you have n squared log n. And yeah, I'll get into why we would need to calculate time complexity in a bit, but this is basically how you calculate your time complexity. Um, with like more complicated problems, there might be amortization or other really weird things that you don't need to worry about for now. You just need to know like the time complexity of your program is generally going to be multiplying all of the for loops that you would need together. So yeah. So let's do let's play a game. So I will show you a code and you will tell me what the time complexity of that code is. Okay. Are you guys ready? Okay. What is the time complexity of this code? Okay, yes, that's correct. It is n cubed. Okay. Are you ready for the next one? Uh, okay. Here's the next one. Yes, Tony, it is n cubed. But why is it n cubed? But it starts at I, right? It starts at I. So why is it n cubed? Well, okay, so n cubed, not n cubed, n cubed. Um, okay, so this is n cubed because um if you look at like the structure of the code, it looks like it might be faster than n cubed because it's starting from I, which means it's cutting on a lot of operations. But if you think about it, um, this actually still takes n cubed operations because if you consider like the total number of operations that this will have, it'll be about n cubed over 6. N cubed over 6 is still equivalent to n cubed because we care about the magnitude. The constant factor doesn't matter. So n cubed over 6 amortizes, or doesn't amortize, but the magnitude of n cubed over 6 is O of n cubed. So the total time complexity of this code will be O of n cubed. Does that make sense to everyone? What doesn't make sense to you? Ray, what doesn't make sense to you? But like explain what doesn't make sense to you.
Really,
Like,
everything.
okay, so I guess I'll explain time complexity again. So okay, so time complexity is a measure of the magnitude of the number of operations that this will take. So basically, you don't care about your constant factors and you don't care about lower degree terms. So let's say like your program takes around 3 times n operations, then the time complexity of that program is O of n. Um, um, basically, this like it basically helps you measure about how many operations that your program will take. So if um, basically, yeah, so it's like approximately how many operations your program will take. So the way you calculate it is you basically multiply all of your for loops together. So if your first for loop will go with n operations, your next for loop will go with n operations, and your next for loop will go n operations. Then if they're nested together, then your total time complexity is n cubed because you have 3 for loops. N times n is n cubed, right? So that's why in the first example, if you look at these 3 nested for loops, this would be O of n cubed because all of these for loops are nested together. So you multiply them together. That's why it's n cubed. In the next example, it's still n cubed because even though you're cutting on the constant factor, it's just a constant factor. You ignore that in your time complexity analysis. So you're still going to have a time complexity of n cubed. Does that make sense? Okay. Oh, so if you're wondering what the difference between the first and the second one are, I can annotate it for you. In the second one, um, this and this are the differences. It starts at I instead of, in the first one, it started at 1, and the first one, this started at 1 as well. So that one's very straightforward to be n cubed. But if you look at the second one, this starts at I. So it actually starts before 1, or it starts after 1. So it has um, other things. Yeah. Okay, I can go back. So here it starts at 0, and here it starts at I and J. So yeah, that's the difference. Okay. Yeah. So why would we need to calculate time complexity? Well, time complexity can be useful. Time complexity would be very useful for a variety of reasons. In the first, first, time complexity can tell you whether your code works even before you code it. So if you can tell that your code doesn't work, like let's say your algorithm is n squared time, but n is like really big and n squared will not work, then you won't even need to code it up, and it'll save you a lot of time. Second, it can tell you like whether you need to optimize your code or think of another algorithm. For example, again, let's say your code is n squared and n is really big, so n squared won't work. Then you might think, oh, how do I optimize this? Or like, do I even need to optimize this? Like, it'll tell you whether you need to optimize your program or whether you need to think of another algorithm. And another reason, um, okay, so if you're confused of what big O notation is, big O notation is basically a way to like measure your time. It's basically the way you write your time complexity. Instead of saying my code takes n operations approximately, you say, oh, my code is O of n. That's basically this way of saying it. So instead of saying my code is my code takes n log n operations approximately, you say my code runs in O of n log n, basically. Um, it's just like the notation. It's just a way to say it. Yeah. Okay. So yeah. So the third case is like more common when you go higher up, but when you're given your constraints for the problem, it can often give away what the intended time complexity of the solution is. So if n is like 10 to the 5, then it'll give away that your running time should be something around O of n or O of n log n or something like that. And that'll help you narrow down the amount of algorithms you will actually think about using. This is why you should always think about the time complexity of your code before you code it, because it can save you so much time. And instead of just like randomly submitting your code, not knowing whether it will time limit exceeded, you can always predict it before you even submit it. So yeah, does everyone understand this? Okay, if this makes sense, then we can move on to our next topic, which is simulation. So simulation is essentially like it's the easiest type of problem, which is essentially where they ask you to find the result after the end of a certain process. So these do not usually require you to think a lot because you just need to implement the process described. Sometimes you need to make some observations about the problem in order to speed up the simulation. Like for example, if you have like a problem that looks like simulation, but the time complexity of directly simulating is not good enough. Like if you calculate the time complexity of simulation, right? You think, oh, it'll take 2 for loops of size n, which it'll take n squared time, but n squared doesn't work. Then you need to think of another solution besides simulation. So yeah, calculating time complexity is very important. If you sometimes simulation still works even though the time complexity doesn't allow it, simply because there are observations that you can make about the simulation that allow you to speed the simulation up a lot. Like for example, if the last few operations do nothing, then you can terminate your process early and potentially save a lot of time. And this can help you a lot when you're simulating problems. Yeah, and it's actually the solution to one of the practice problems later. Um, yeah, are there any questions? Oh, I should also note, in order to determine whether your time complexity works, you basically calculate the time complexity at n. So let's say your program runs in O of n squared. You basically calculate n squared and you compare it to the following number. You compare it to 5 times 10 to the 8. That's basically the number that you compare your answer to. So for example, if n is 10 to the 5 and your program is O of n squared, that means that n squared is 10 to the 10, which is bigger than 5 times 10 to the 8. So yeah. Um, okay. Does this make sense to everyone? Okay. Um, okay. Let's go to our next topic, which is brute force. So brute force or complete search. Brute force or complete search is basically where you have a problem where you need to optimize something or you need to basically like determine the number of things that work. And the easiest way to do this is basically to go through every single possibility and determine the best one, or just determine the number that work. And so this idea of going through every single possibility is known as complete search or brute force. Um, yeah, does that make sense? Is there any difference between simulation? So simulation is basically where they give you a process and you have to basically try to see what happens after the process is over. Complete search or brute force is basically where you check every single possibility. Like, for example, if you're trying the best pair, then you go through single pair and you check if it works and you add it to the answer if it does work. Um, yeah. Complete search should always use more time complexity than other ways, because if another way uses more time than complete search, it's completely dumb because you can just go through every single possibility. So whenever you're trying to think of another way of doing a problem, it should always be faster than your complete search, because if it's slower, then you might as well do complete search anyways. Yeah. Does that make sense to everyone? Um, okay. So sometimes you need to optimize your complete search algorithm. That means that, like, sometimes your complete search is by itself won't be sufficient to get all of the points for a problem. Like, for example, again, if your complete search is like n squared and n is 10 to the 5, you won't be able to do that. So often you need to prune your complete search and reduce your time complexity. And how do you do that? Well, there are a lot of ways to make observations that can help you speed up your complete search. For example, what states do I really need to consider? Like, there are some states that are obviously suboptimal, and those states you can just ignore them. And if you ignore them, sometimes they constitute like the vast majority of all cases, and it can reduce your time complexity by a lot. Another way you can optimize this is you can check like what properties must it satisfy to be completely optimal. Like, for example, in order for something to be optimal, it must be even or it must be odd or something like that. And just noticing that it must be even can reduce all of the things by half. And then once you notice that, you might be able to do something else with your search. So yeah. Um, does this make sense to everyone? Okay, so yeah. So here's a practice problem for a complete search. So this is actually a USICO problem that appeared in the past year. Um, okay. You can, okay. So yeah. So here's a practice problem. You have an array, like this is basically like the shortened version of the problem statement. So here n is 10 to the 5 and the sum of all of the numbers in the array. Okay. Actually, I'll send the link in chat. So yeah. Yeah, here you can read the problem, but essentially it's saying you have an array of numbers, and in one operation, you can take two adjacent numbers in the array and replace them with the sum of their original numbers. And you basically want to find the minimum number of operations it takes so that all of the numbers are the same. And the constraints for this problem are n is less than or equal to 10 to the 5. And this is important because that means that n squared will not work. And then you have the sum of all a of I, which is basically the sum of all the numbers is less than or equal to 10 to the 6th. Yeah, and this is an interesting constraint within the problem, and it should give you a hint. This should give you a hint. Yeah. So let's say we wanted to do a complete search. How would that work? Well, if we did a complete search, that means that we would basically have to check each number that, okay, well, we would basically have to check each number, like for example, 1, 2, 3, 4, 5. Let's say we're checking 3, right? Now we want to basically make each number equal to 3. Well, how do we do that? Well, we want to basically keep adding the number to your current number until it's equal to 3. And then after that, you go to the next number and you keep adding until it's equal to 3. And then you keep going that. And then you can calculate the number of operations that will take. And then you do a maximum over all of that, right? But this won't work. And this won't work because the sum of AFI goes all the way up to 10 to the 6. So theoretically, you could go all the way up to 10 to the 6, and that could be the only answer. And if that's your only answer, then you're taking 10 to the 6 times 10 to the 5 operations, which is way too much, which is way more than 5 times 10 to the 8. So you're not allowed to do that. So you have to speed up your complete search somehow. Yeah. So does anyone have any ideas about how you would speed up that solution? What do you mean by try to add every pair? With logic? What does that mean? Um, okay, so if you try to add the smallest pair together, that won't necessarily work. For example, let's try to create a counter case to that. And this is a very common technique. Like if you have an idea, you want to basically see whether it works. And the easiest way to see whether it works is to try to construct a counter case. And if you run into a problem constructing a counter case, try to use that problem to prove that your solution is correct. So let's first try to construct a counter case with this problem. So for example, Tony said 7, 3, 5, 5. What will your program do? Your program would first merge these two. So you use 7, 8, 5. Now it would merge these two. So 7, 13. And then it would merge the whole thing. So 7, 20. But this is definitely not the optimal solution. You could just merge these two instead. And then that would be better. So now you can like reject your solution and then think of another one. Yeah. Um, okay. So if everyone's struggling, let me give you a hint. So hint 1. Consider the sum. Consider the sum of all of these. What does that sum satisfy? Like, what is the sum at the end? What is the sum at the beginning? How do they compare? And how do you use that to your advantage? Well, okay, do something is very ambiguous, but max element is also not very, um, yeah. Okay, yeah, divisibility is very close. So the idea is to notice that the sum of AI is an invariant. It's constant throughout. Because if you think about like any case, like for example, the counter case before, whenever you take two elements and you take their sum and you replace them, so you have 10, 5, 5, the sum remains the same. The sum over here equals to 20, and the sum here is equal to 20. And this is really easy to see because when you're deleting the two elements at the start, you're deleting the same number as the number you're adding back. So the amount you're adding back is equal to the number that you deleted. So the sum always stays the same. So how can we use that to our advantage? Well, one way to take advantage of this is to look at what happens at the very end. At the very end, what are the numbers going to be? At the very end, they're all going to be the same. They're all going to be x and x dot 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 x. So what does that say about x? Well, that means that x times some number that we don't care about is equal to the total sum at the very beginning. That means that there are only a limited number of x that can possibly work, right? And yeah, and the limited amount of x that can actually work is about 200. So there are only about 200 x that could possibly work. So now what do we do? The way you get 200, you have to kind of like memorize this or do something like that. But basically it's the number of divisors of 10 to the 6. So or the number of divisors of like the maximum possible number of divisors of anything less than 10 to the 6. So I think that number is like 2 to the uh 2 to the 5 times 3 to the 4 times 5 to the 4 or something like that. I don't remember exactly what it is, but something like that. And like the total number of factors it has is like something like 240, I think. So yeah, it's about 200. Okay, so what do we do with this? Well, we can just do a brute force, right? We can essentially just do run a brute force on all of this. And then when we do that, we can just find the answer. So because there are only about 200x, you can basically go through each individual x and check whether it works. And the way we can check whether it works is if we consider what happens at each index. When you combine them, what happens is you have a bunch of ranges that come together. And when you have a bunch of ranges that come together, you can basically keep going. If you like start with 0 and then you add something and then add something and then add something and then add something. And once your total sum is equal to x, let's say the total sum is equal to x here. Now you make the sum 0 again. You get rid of this first part and then you start considering from here. And once you can, oh, so X is the final number in the array. So at the end, you'll have a bunch of numbers that are the same, and let's call that number X, right? So when you do that, you can basically check if this is equal to X. If the sum is equal to X, then you make it 0, then you do it again. And then whenever you go above X without being equal to X, then basically stop. And the solution is basically to just try a bunch of different X, and you just find the maximum possible answer from your X. And the way you can find answer from X is basically that if you have X things over here and you have a sum over here, the total number of elements remaining is sum over X. And in each operation, you're deleting one element. So the total number of operations you require is this number. And you can find this number over all working X, and then you can find the maximum. Yeah, this problem is very hard. But I just use this as an example of like how you can use observations about the problem to optimize your complete search until it works. So yeah. Yeah. Okay, so now if you don't have any questions anymore, then we can do the then we can do the challenge problems. So here's the solution. I just explained it, but if you wanted to read it, here it is. Yeah. So the first challenge problem is simulation. And the second challenge problem is also simulation, and the third one is complete search. And I'm breezing through these slides right now because all of them are on code forces. So if you go to the group and you look, there should be a second contest over here. And here you will find all of the problems from day 2. Yeah. Yeah. Okay. If you guys have any questions, then you can ask me about them now. But if, yeah, I'll just help whoever I need to help during this time. So, okay, it's 6 now. So if you have any more questions, you can stick around. But if not, then I guess class is dismissed. So, yeah.